Hi, I'm Professor Melko, Chemistry PhD, and today I'm going to lecture on periodic trends, like atomic radius and ionization energy, and then going to abbreviated electron configurations and how adding or removing electrons can alter that abbreviation. So let's start the lecture. Periodic table is organized so properties follow trends as you go across the periodic table or up and down in the periodic table, and this was sort of Mendeleev's whole idea, is that organizing the elements in certain groups gave this table structure. And so now that the elements are in certain groups, they will have similar properties. One example of this property that follows some certain trend is atomic radius, and this is how large the atom is. Okay? And the trend in the periodic table is as you move left to right, they get smaller. As you move top to bottom, they get bigger. And so that's sort of symbolized here. As I move from hydrogen to helium, the atom's getting smaller. As I move from hydrogen down to cesium, the atom is getting much, much larger. Plenty of people just sort of memorize this trend, but I think it's better to actually understand the reason for the trend. And the reason has to do with electrons and energy levels. Atoms get smaller going up a group, or I guess I should say the reverse, right? As I go down this group from hydrogen to francium, the atoms get bigger. And the reason for that is I have this dense nucleus, right? If we think of this about the time of Bohr discovering these orbits, we have this dense nucleus here, and there's electrons orbiting it. Okay, if there's only 2 electrons, they both can fit in this first orbit, right? Hydrogen only has 1, so it's in the first orbit, and that is the extent or size of that atom. Now, as I go down, I'm adding many more electrons. Down here at francium, I have 87 electrons. So there's going to be a lot more orbits required to hold these electrons. So now francium is larger than hydrogen because it needs these extra shells or energy levels. Okay, so understanding as I go down the periodic table, I'm adding electrons, meaning the atom is going to get bigger. That's the trend for atomic radius. Left to right is a little harder to understand, but not beyond us. Atoms get smaller going left to right because the number of protons is increasing without adding an extra shell. Okay, so you're adding protons, which means electrons are also increasing, but you're not adding a whole new shell, right? As I move left to right, okay, maybe I'm in this third row, right? So let's just think about this third row, which means, right, I'm in some third energy level. So let's say this is the first energy level, this is the second energy level, and this is the third energy level. And of course, we learned in previous lectures there's sub-levels, meaning each of these levels is sort of divided up into sub-levels. Okay, but this third energy level is further out. Now, all the electrons, whether it's 1 for sodium, that is in this third row, okay, we'll learn later on valence electrons, sodium has 1. It lives in this third shell, okay? But as I get to argon, now I have 7 more electrons that have to go in this shell as well. And I'll draw a few of them here. I haven't made the atom any bigger, right? But actually I've made the atom smaller. And the reason for that is because the protons are also being added in the nucleus. Okay, so the positive charge in here is increasing. As I move left to right, the number of electrons in a certain shell is increasing as I move left to right, and opposite charges attract. So as I move left to right across the periodic table, I'm increasing the positive charge, which means I can pull on those electrons and attract them to myself stronger. So as I move left to right, the atoms are actually smaller because of this extra pull that the nucleus is having on these electrons. So left to right, atoms get smaller because of this attraction. Top to bottom, atoms get larger because you have extra shells. So let's take a moment and try to practice this in the following problem. Feel free to pause the video here and try to solve it yourself. I'm going to proceed and solve it. Which element in each pair has the larger atomic radius? Sodium or cesium? Sodium. Here's cesium. Atoms get bigger going down, so cesium is larger. It has 6 shells since it's in the 6th period. Sodium only has 3. Okay, so the cesium atom is much bigger. potassium compared to calcium. Those two are neighbors right here. Remember, as I said, we move left to right. The atoms get smaller, which means potassium is larger. Fluorine versus sulfur. Okay, these are sort of catty-corner to one another. Fluorine is further to the right, which means it's smaller, and it's closer to the top, which means it's smaller. So sulfur, on both accounts, is larger. Lastly, iodine, shown here, and rubidium, over here. Iodine further to the right, it is smaller, so rubidium should be the larger atom here. Okay, so that sort of concludes the mini section here on atomic radii. Let's think about predicting other properties. Other properties might be something like melting point, boiling point, or density. And as I said, things that live in the same group, like the alkali metals shown here, will have similar properties, and those properties will change more or less uniformly as I go down the group. So as I go down from lithium to sodium to potassium, the melting point, lithium, sodium to potassium, is decreasing. I would expect rubidium to be even lower, it is, and cesium to be even lower than that. The density increases, then steps back a little bit, then increases, okay? A little bit of a step back here, but overall it's increasing. So if I wanted to think about francium, okay, that lives right under cesium, what might I predict for the properties of francium? The melting point I would expect to be even lower than 28.5 degrees Celsius. The density I would expect to be higher. Just following that periodic trend. And indeed, that's what we see. Francium has a density greater than 1.93 and a melting point less than 28.5 degrees Celsius. Okay, so you can always use these periodic trends to make predictions about certain elements based on your understanding of the other elements in that group or family. That's a physical property like melting point or density. Chemical properties are also going to be predicted. Okay, we talked about physical versus chemical change and physical versus chemical properties a few lectures back, so go back and review that video if you don't remember. Chemical properties are when chemistry happens and you have to rearrange atoms. So these alkali metals, when they react with oxygen and bond with oxygen, they bond in this sort of 2-to-1 ratio. Okay, what do you think the chemical formula is for a compound where francium combines with oxygen? Well, all of these are 2-to-0. Francium is in that same group, so I'm willing to bet it's going to be 2 franciums for every oxygen, and that's exactly what chemists see. Now, there's actually an element under francium yet to be discovered. That's where you come in, melkonium. So get out there, discover this next alkali metal. We know its properties. It's going to live right here. It's going to react with oxygen to make Mk2O. It's going to have a melting point less than 28.5 degrees Celsius and a density greater than 1.93. We know all the properties. You guys just have to get it out there and discover it. And of course, name it after Prof. Melko. Okay, moving on, we're going to talk a little bit about abbreviated electron configuration. We know the periodic table is organized so that things fall into groups with the same properties, and this is really dictated by the electrons. Okay, a lot of times we talk about these elements living in certain blocks of the periodic table, which is based on their outermost electrons. So this right here on the left is the S block. These elements' outermost electrons are in an S sublevel. We talked about this before in writing electron configurations. This is a slide we've covered in a previous lecture, so I'm going to go through it a little quick. You can go back to that lecture and spend time writing these electron configurations. Basically, you count, for example, bromine, how many electrons it has, 35, and you write out the sublevel ordering, increasing in energy. Then I go through and add these 35 electrons to get the electron configuration as shown here. Okay, we don't need these extra sublevels here because I've run out of the 35 electrons. So that's the electron configuration for bromine. Abbreviated electron configurations are nice because you might not want to write out this big long trail of letters and numbers. So chemists came up with abbreviated form, and it's abbreviated by clumping some of these sublevels together. And the rule is as follows. For bromine, or for any element, you go back through the periodic table to the previous noble gas. Okay, so remember the noble gas is this last column here. The noble gas before bromine is argon. And I'm going to use the noble gas in brackets to symbolize 18 electrons. Okay, so look at the atomic number. That's how many electrons I'm replacing. So I can take out the first 2, 4, 10, 12, 18. I can replace all of those just by writing brackets argon. Okay, and then I'm going to keep all of these extra electrons and just write them after argon. Okay, that's what's shown here. Argon 4s2, 3d10, 4p5. Okay, so that's the abbreviated electron configuration for bromine. You're just backtracking through the periodic table to the previous noble gas and replacing that many electrons. Now, sometimes you'll see exceptions to this ordering of the subshells. I just want to bring your attention to specifically copper, silver, and gold, these coinage metals here. There are exceptions. As you fill these up, you're not going to get S2D9. Transition metals are a little funny. It turns out that it'd rather have a full 10 electrons in the D sublevel. Okay, so usually we just order these things, adding the electrons in sequential order to the higher and higher sublevels. If you did that, you would get S2D9 for these three elements. In actuality, it's S1D10. So those are sort of the three exceptions you need to keep in mind when writing electron configurations, either full or abbreviated. If it's for these three elements, just remember that. Let's take a second and do a practice problem. Try to write the full and abbreviated configuration for nitrogen and magnesium. Pause the video here and try for yourself. Nitrogen has 7 electrons. I know the sublevels are ordered 1s, 2s, 2p, 3s, 3p, 4s, 3d, so on and so forth. But I'm going to stop here because I know how far I have to go. If you don't, feel free to write out more sublevels. Now I'm going to add these 7 electrons. Each s sublevel holds 2, so there's 2, there's 4. I have 3 electrons left. They can fit in this p sublevel. So the full electron configuration for nitrogen is 1s2, 2s2, 2p3. Remember the shortcut, find nitrogen on the periodic table, and simply count through the elements you have to pass through. In the first period, you have to pass through this s block. Helium kind of lives here for this demonstration. For the first period, I have to travel through this s block, and I have to go 2 spaces, 1s2. After that, I have to go through this second s block, and I have to go through 2 elements. I enter the p block of this second row, 2p, and I have to go 1, 2, 3 places, 2p3. So either one of those is how you can come up with this electron configuration. Abbreviating it, I'm going to go back from nitrogen to the previous noble gas helium and see that I can replace helium's atomic number is 2 electrons. So I replace the first 2 electrons by writing out helium. It's not much of an abbreviation, but this is what the abbreviated configuration would be. Now let's consider magnesium. Magnesium's down here with 12. I can count through the periodic table again. 1s2, 2s2. This time I make it through all 6 of 2p area. Now I'm entering 3s. And I'm going to the second spot. So here's magnesium's 3s2. Abbreviated, I can come back and replace with the previous noble gas before magnesium, counting back from 12 to 11 to 10, I get to neon. So the abbreviated form would be neon, where I can replace the first 2 for 10 electrons. So I'm replacing all of this by brackets neon. And so the abbreviated configuration is neon 3s2 for magnesium. Now, turns out this abbreviated system is actually good for showing how many valence electrons. So using this noble gas core, you're sort of taking all these inner electrons away and only writing out the outermost electrons, which is what we call valence electrons. And these are important in chemistry because most chemical reactions are driven by the valence electron count. How many valence electrons does an element have? How many does it want to get to? And that'll describe what it reacts with and how many atoms it reacts with of that other element. Okay, during chemical reaction, pretty much only valence electrons are involved. And at this stage of chemistry, we're going to assume that only s and p electrons matter. So d electrons and f electrons are a little, funny about this. So for this purpose and for these practice problems, we're just going to call the s and p electrons valence. So the outermost s and p electrons are our valence electrons at this stage. There's a shortcut, of course, to counting up valence electrons. You can consider what row of the periodic table it is. Remember, we're just worried about s and p here. And sort of count left to right. So for carbon, how many valence electrons does it have? Don't count the transition metals. 1, 2, 3, 4. Carbon has 4 valence electrons. Everything in this group has 4 valence electrons. Oxygen, 1, 2, 3, 4, 5, 6th column, it has 6 valence electrons. Fluorine, 7th column, 7 valence electrons. Helium, or I should say neon, 8th column, 8 valence electrons. Okay, so that'll work for anything besides helium, really, which only has 2 valence electrons. But that's sort of a shortcut for the S and P valence electron counts. Now, one way we symbolize this number of valence electrons that is useful for drawing chemical structures is something called the dot formula. And we'll work more on this later in the semester, but we want to introduce it now while we're talking about valence counts. The dot formula shows an element symbol surrounded by its valence electrons, where one dot is one electron. So we're going to symbolize electrons with dots. Phosphorus has the electron configuration brackets neon, 3s2, 3p3. Okay, so these superscripts here, remember, are the electrons in this abbreviated notation. They're the valence electrons. So there's 5 valence electrons total. I'm going to write the dot formula by writing the symbol, phosphorus, capital P, and surrounding it by its 5 valence electrons in this case. And I don't add them all to one side. I go through the following process. I write 1 on the right, and then go around in a clockwise fashion. 1 underneath, 1 to the left, 1 on top. That's 4. I have a 5th, so I can pair it up on this first side. If I had 6, the next one would go at the bottom. 7th, that would then go on the left. 8, that would go up top. So dot formulas are pretty easy at this stage. Just write the symbol and start surrounding it in this clockwise motion. 1 dot on each side. Then you can start pairing them up if you get more than 4 valence electrons. So take a second and try this yourself. Write the dot formula for barium. The symbol for barium is capital B, lowercase a. It is in this second column here, so it has 2 valence electrons. First valence electron, I'm going to make a dot on the right side. The second, I'm going to make a dot at the bottom. That then is my dot formula for barium. Just that easy. Now, the last trend we're going to talk about here is ionization energy. Okay, we talked about atomic radii, right, and how that changes moving across and down the periodic table. We also want to introduce ionization energy. And this is how much energy it takes for you to go in and pluck an electron out of an atom. Okay? You can imagine this is going to be harder the closer that electron is to the nucleus. Remember, the nucleus has these positive protons that it's pulling on the electrons with, right? That positive proton attracts that negative electron. Opposites attract, right? So the closer that electron is to the nucleus, the stronger that proton is holding onto it, and you have to use more energy to, remove that electron from that nuclear pull. So closer an electron is to the nucleus, the more energy is needed to remove that electron, right? So the ionization energy is increasing as I go up the periodic table, right? Because the atoms are getting smaller. Think back to our trend of atomic radii, right? As I go up, the atoms are getting smaller, meaning the electrons are closer to the nucleus, meaning it's going to be harder for me to remove that electron. So the ionization energy, is how much energy you have to spend removing the electron, that's going to be larger for these smaller atoms. So ionization energy increases as I go up, and for the same reason it increases left to right. Okay, again, left to right, these atoms are getting smaller, the electrons are closer to the nucleus, so it requires more energy, or a higher ionization energy, to remove those electrons. When I remove the electrons, I can be left with what's called an ionic charge. So imagine you have a atom of calcium, or barium, I suppose. We just did that example. It wants to have, or it does have, 2 valence electrons. Maybe I remove one of these electrons. Okay? It's now no longer neutral, because I needed that electron to exactly balance out the positive protons. Now that I've removed an electron, I have more protons, positive, than electrons, negative, and I'll have a positive charge overall. Okay? Species that aren't neutral but have a charge are called ions. And so you can develop a charge on these ions. If it's positive, we'll write this out as a positive charge. So imagine sodium that I removed 1 electron from. I can write sodium 1 plus, or usually that'll just be written as sodium plus. If you think about barium, I can remove 2 electrons, both valence electrons, and write barium 2 plus. So the charge of an ion, it turns out, is related to the number of valence electrons. Barium had 2. It's going to make a 2 plus ion because I can remove both of those valence electrons. Sodium only has 1 valence electron, so it becomes sodium 1 plus. The whole driving force here on the periodic table is the effort to get to this noble gas configuration. Okay, noble gases are so-called noble because they're happy, they're elite, right? They're also inert, they don't react. Why? Because their electron shells are full, right? So remember this idea of electron shells, and a certain number of electrons sort of fill up those shells. The noble gases have full shells, they're happy, they don't have to barter with any other elements to fill up their shells. Okay, all other elements are trying to achieve this noble gas configuration. Okay, so think of barium again. What noble gas am I closest to? Well, xenon is just 2 spots back, 56 to 54. So if I lose 2 electrons, okay, I am essentially then at the electron configuration of xenon. Right, so barium's electron configuration is xenon 6s2. If I lose those 2 electrons, now I look just like xenon and I'm happy. And this is what drives a lot of chemistry. Right, so barium is going to develop this 2 plus charge because now it looks just like a xenon electron configuration. So these group 1 metals tend to form 1 plus ions, shown here. Group 2 metals tend to form 2 plus, like barium we just talked about. Transition metals are a little funny. Some of the charges are, predictable, some aren't. Some other ones that are predictable are the halogens. I'll write H for halogen here. They all become -1s. Why? Because they only need 1 more electron to get to a noble gas configuration. Oxygen, sulfur, selenium, these in group 16 need 2 electrons. Each electron is negative, so they develop 2 minus charges. Right, because they have to go 1, 2 steps over to the noble gas, 1, 2 steps, so they develop these 2 minus charges. So you can look at the periodic table and predict the ionic charge that will develop on any given element, although the transition metals and these rare earths are hard to predict. So you might be asked to write out this new abbreviated or full electron configuration of these charged species, these ions. Okay, so think about the sodium ion. Remember we said we can remove one electron, so we do just that. We look through its electron configuration and you remove the outermost one, that highest energy one. Okay, so I just removed this 3s1. So writing sodium plus is just 1s2, 2s2, 2p6. Okay, and this turns out to be the noble gas configuration, or the electron configuration of the noble gas neon. Correspondingly, oxygen has to move to the right on the periodic table, gaining electrons. Since electrons are negative, it's gaining negative charge. We write that as 2 more minuses. So this electron configuration of oxygen, I have to add 2 electrons. So this 4 can become a 6 because I've added 2 more electrons. The charge overall is negative with the addition of electrons. It's a little counterintuitive, but practice these and you'll get it. So here's the electron configuration of oxygen 2-. If I'm abbreviating it, that is also neon. That is the element, the noble gas, whose electron configuration oxygen has now accessed. So let's end with a practice problem. Feel free to pause the video here and try to write the abbreviated electron configuration for this ion. Se is selenium. It lives right here. The 2- means I'm adding 2 electrons, meaning I now am going to look like krypton. So the shortcut here is pretty straightforward for writing the abbreviated electron configuration. Usually we look backwards to the previous, but I've just assumed with these 2 extra negative charges, the configuration of krypton. So I don't have to go back to argon's noble gas configuration because I am krypton now. I have the same electron count as krypton. It is organized the same way, so the configuration is just brackets krypton. That does it for today's lecture, where we covered these electron configurations for ions, and we also talked about atomic radii and ionization energy in the context of periodic trends. Future videos, I'll do some more practice problems like I did today. As always, feel free to subscribe to this channel for more videos like this and lectures, or check me out on Twitch for office hours where I do practice problems like the one shown here, review sessions for exams, and answer whatever chemistry questions you might have. See you next time.